Within the sport of golf, many basic physics concepts and laws can be observed and proven. In terms of Newton's first law, stating that an object in motion will stay in motion and an object at rest will stay at rest, one can simply look at this golf putt. Following Newton's first law, in absence of an unbalanced force, this golf ball remains at rest. Once the force of the putter is exerted on the golf ball, the ball moves until the friction of the grass eventually brings it to a stop. Although not shown in this instance, if the golf ball were on a flat, frictionless surface, it would remain in motion at a constant speed in a straight line. This idea of inertia can also be seen in the shot by Phil Mickelson. As his club goes underneath the golf ball, the inertia of the ball, dependent on its mass, keeps it at rest, just as silverware on a table stays at rest when a tablecloth is pulled out from underneath. Another physics aspect can be seen in golf swings, like that in the movie Happy Gilmore. The velocity or directional speed of a golf club is equal to the sum of the combined velocities of the hands, elbows, shoulders, and rotation of the body. As shown in this situation, a running start increases this golfer's club velocity from its usual when standing still, as the greater velocity from the running start adds to the total of the sum. By the same rule, the golf ball goes further than usual as the sum of energy exerted upon it includes the added speed of the running start. In terms of frames of reference, with a golf club velocity of 100 miles per hour and a running start 4 miles per hour, the club is moving at 100 miles per hour relative to the body, but moving at 104 miles per hour relative to the ground. Newton's second law of motion states that the acceleration of an object is directly proportional to the unbalanced force acting on it and inversely proportional to the object's mass. In other words, this relationship can be defined by the equation F equals ma. By this equation, if the average immediate acceleration of a golf ball during a tee shot is about 430 meters per second squared, and the mass of a golf ball is about 0.046 kilograms, then the average applied force on a golf ball is about 20 newtons. In this way, one can see how ball speed in golf is much faster than that in other sports. If the identical force of 20 newtons was applied to a 2-kilogram bowling ball, for example, the resulting acceleration would be a much smaller 10 meters per second squared. Again, this reiterates the principle of Newton's second law, that as mass increases, acceleration decreases. There is also another force present within these tee shots that you cannot see. This is the force of gravity. This force of gravity, also known as weight, depends on the mass of an object and the acceleration of gravity, 9.8 meters per second squared. Let's say one of the golfers in this clip is 80 kilograms. If you multiply 80 kilograms by 9.8 meters per second squared, one can discover that the force of gravity on the golfer is 784 newtons. Likewise, a 0.046 kilogram golf ball sitting on a tee multiplied by 9.8 meters per second squared would have a force of gravity of 0.45 newtons acting upon it. In this case, the tee also exerts an equal and opposite force up towards the ball, countering the downward force of gravity, giving it a net force of 0, and a 0 acceleration. Additionally, the ground exerts an equal and opposite force upward to counter the combined downward force of gravity on both the tee and the ball. In further reference to the force of gravity, as seen in this lob shot, the ball begins to accelerate back to the earth after it has reached its apex. As stated by Newton's second law, where there is acceleration, there must be an unbalanced force acting upon it, the object, which in this case is gravity, accelerating the ball back to the earth at 9.8 meters per second. Newton's third law of motion asserts that forces come in pairs, or, for every applied force, there is a resulting equal and opposite reaction. In this view of Tiger's swing, as his club hits the golf ball with a force of 20 newtons, the golf ball exerts an equal force of 20 newtons on the club face. With an equal and opposite force in this situation, one might wonder why the ball is able to be moved. The ball moves because the two equal and opposite forces are acting on different objects. Furthermore, the fact that the golf club has more mass than the golf ball enables the golfer to apply such immense acceleration on the ball, propelling it forward. Friction plays an important aspect on greens of golf, as they help determine how fast or slow a putt might be. The more friction applied by a green on the golf ball, the more the golf ball slows down, eventually coming to a stop. One could discover the coefficient of sliding friction on the green with the equation force of friction equals the coefficient of sliding friction, mu, multiplied by the normal force on the golf ball. The force of friction in these putting clips would be equal to necessary force to move the golf ball at a constant speed, which in this case might be about 0.25 newtons. The normal force on the golf ball, which is equal to the downward force of gravity on the ball and upward force of the ground, can be found by multiplying the 0.046 kilogram mass of the ball times the force of gravity equaling 0.45 newtons. Finally, the coefficient of friction can be found by dividing the 0.25 newton frictional force by the 0.45 normal force equaling a mu of 0.56. When putts like these are moving on an incline or decline, the mu can be determined as well, with the normal force simply readjusting perpendicularly to the new plane and the force of friction readjusting parallel to the new plane. Altogether, as the mu increases, friction increases, causing the golf ball to slow down and stop more quickly. The physics concepts of kinetic and potential energy can easily be observed in the golf swing. As this golfer takes his backswing, rotating his body and taking the club to its maximum height, he is increasing the potential energy of the golf club. This potential energy, or energy associated with position, is then transferred into kinetic energy in motion, as he exerts force accelerating the club towards the ball. Altogether, the total sum of energy remains constant as the kinetic energy increases following the decrease in potential energy from the top of the backswing. Likewise, right before the club face makes contact with the ball, the total amount of kinetic energy within the club is equal to the previous total amount of potential energy prior to the club accelerating towards the ball. As seen in this clip of a golf ball being compressed, the kinetic energy from the club is subsequently transferred to the golf ball, producing its initial projectile velocity. The rest of the kinetic energy on the club causes it to rotate to its maximum height after contact. In this situation, the kinetic energy of the ball can be determined through the equation kinetic energy equals 1/2 times mass times velocity squared. The ball speed in this instance is 55 meters per second, which squared and then multiplied by the 0.046 kilogram golf ball mass and then by the 1/2 value equals 70 joules of kinetic energy. In this clip of a very vertical shot, gravitational potential energy can be seen more clearly. While the ball is decelerating as it rises nearing its apex, kinetic energy decreases, turning into gravitational potential energy, maintaining the total energy sum. When the ball reaches its apex, the gravitational potential energy reaches its maximum, while the kinetic energy reaches zero. As the ball comes back down, accelerating by way of gravitational force, kinetic energy increases while the gravitational potential energy turns to zero. In this case, the gravitational potential energy can be calculated by the equation gravitational potential energy equals mass times gravity times height. The mass of the ball, 0.046 kilograms, is multiplied by gravitational acceleration, 9.8 meters per second squared, and by the height, which in this case might be 3.5 meters. Here the gravitational potential energy would be equal to 1.6 joules. In regards to projectile motion, objects travel in bowl-shaped trajectories known as parabolas. Golf balls, however, do not follow a true parabolic path because of factors such as dimples in the ball, air resistance, and spin imparted by the golfer. If a golf ball were to hypothetically follow a perfect parabolic path, one could calculate the distance traveled from the origin and time of flight with the given launch angle and initial velocity. Instead of going into depth into how this calculation works, we will leave an example problem in the script for Mr. Hogan and show you this video.
And wayward tee shot ends up just and when I mean this is steep, I mean just short, and he's got to play a backward
Fuck man, I'm drunk.
shot.
I'm drunk.
And he pissed. Fuck, I fucking hope you fall in, man. I hope you
Joe,
do.
don't say that.
Alright, okay. Just get it up.